Hello, good morning everybody, and good afternoon to our friends over in Europe. Welcome to this webinar on the 7 considerations before you refresh your F5 or Citrix NetScaler load balancers. I'm Chandra Sekhar, VP of Marketing here at Avi Networks, and I'm joined by my colleague Ashish Shah, who is Director of Product Management. Over the next 40 or 45 minutes, folks, we want to share with you some of the key considerations that you need to be thinking about as you refresh your hardware load balancer, and some of the major questions that you should be asking of your load balancing vendor. So without much ado, let's get started on some background information that I want to provide about Avi Networks before we get started. Okay, so Avi Networks is a software-defined application services company. We provide load balancing, the traditional application delivery services, together with application security and SSL offloading. We also provide unprecedented visibility to applications in the context of the network. Our customers tend to be very large enterprises in financial services, in banking, large service providers, multinational technology companies, online retailers, and so on. We have global operations in the United States, in Europe, and in Asia, both in terms of our R&D facilities, our customers, and engineering and support organizations as well. We were named a cool vendor by Gartner in 2016 in enterprise networking. So one of the things that I wanted to also talk to you guys about is, just by way of context setting, I want us to ask yourself, which one of these statements is true in your environment? So if you look at one of the common complaints that we hear from application teams in a lot of enterprises, it's that it takes too long to provision applications, and they have an extended period of time where they have to wait in order for load balancers and VIPs to be provisioned by the network team. They can't easily let developers or testers use load balancers, and a lot of times that's a problem because developers and testers want to have their own instance of their load balancer that they can play with. So that's an important need for a lot of enterprises. Now, going forward, a couple of other things that we commonly hear, and I want to see if I can get a virtual head nod from you guys on this, is this notion that the network team gets blamed for a lot of the application issues. This is commonly something that we hear where an application has a slow response time, and the onus is on the network team to investigate what went on and come back with a resolution for that issue. They also have the problem of not having easy visibility or tracking of virtual services and pools in their environment. We've heard of administrators maintaining long spreadsheets and sort of painfully updating that every time they have to add new virtual services or pools or pool members as servers. So what else is out there in terms of common issues with existing sort of load balancing capabilities? They are over-provisioned based on the worst-case need. Chances are that you have an HA pair of load balancers that are designed to handle traffic at least about 5x the time that you actually have on the average day. And this is sort of the worst case provisioning of the load balancer. And really, you don't have another choice but to do this because you don't want to be held hostage when you do have that increased traffic that you have to handle. And also, a common problem that we hear from customers is that their scalability is limited by the appliance that they purchased. Essentially, it gives you a ceiling up to which you can scale, and after that, you have to go ahead and buy additional appliances in order to scale beyond. Now, does this sound familiar? You ask for software, and your hardware load balancing vendor says you need to buy a hardware appliance. Why is that? A lot of times, the virtual editions of these hardware load balancing appliances simply do not perform to the scale that you want them to. And a lot of times the hardware acceleration is something that they rely on in order to provide you the performance that you need. And so even if you want that software form factor to address a lot of the newer use cases, the east-west load balancing scenarios and so on, you're going to get pushed a hardware load balancer. The last one is something of a conundrum in computing. If you notice, most of the x86 computing world is used to the notion of Moore's law, increasing processor speeds, providing better performance at a lower cost. Now, that is never true in the load balancing world with the appliances, where each new version of the appliance costs more than the previous one. The most recent case being F5 launched their I-Series appliances, and I'm sure if you look at a refresh of your F5 load balancers, you'll be looking at paying more than the last time that you bought them. So let's take a look at why we are in the state that we are in. So if you look at web-scale computing companies like Google or Facebook or AWS, one of the key observations is that they are able to leverage the power of commodity x86 servers to provide a much more flexible and fluid model for computing. All of the services are highly automated. The provisioning of these servers, the elasticity of the compute infrastructure is all taken care of by those web-scale providers. Now, if you think about the average data center and the amount of x86 computing power that they have, and compare that with application delivery services, these application delivery controllers have been around for a very long time. They occupy a rack in the data center. They're inflexible. They have a rigid legacy model that they use compared to the right-hand side of that picture, where you have a much more fluid model for computing. The load balancers themselves, when they came to be in use back about 20 years ago, if you look at essentially the technology itself, it hasn't changed much in that time. Most of the improvements have been associated with putting faster processing power, better performance. Yeah, I mean, there's been incremental features that have been added to these load balancers, but mostly the architecture has remained identical. The flexibility associated with these appliances is constrained by the fact that they are built on proprietary hardware appliances. You cannot have portability of your applications. If you want to move them to the cloud, you have to choose a virtual edition, and again, pay a lot of money for that. And there's very little by way of automation or telemetry built into these systems. And most importantly, they provide you with a static capacity beyond which you have to buy additional appliances to satisfy your performance or elasticity needs. So let's take a look at an architecture that might help mitigate some of these challenges that you have with traditional load balancing architectures. Avi Networks set out to build a software-driven approach to load balancing. And a lot of times you'll hear vendors say things like, we are software-defined hardware, and you'll hear talk of software-defined this or that. And a lot of times, if you kind of peel back under the covers, you still are dealing with a hardware appliance. Instead, what Avi chose to do is we took this monolithic piece of code that went on a singular hardware appliance called the ADC, and we broke it apart into a logical separation between the control element and the data plane. The control plane is the place where decisions get made about load balancing, about the right place to deliver those services, about the exact application loading, etc. Now, the data plane is the load balancers themselves, and these load balancers can go on a variety of different infrastructure components or environments. And what Avi chose to do is create these very low footprint, high performance load balancers that can be installed on bare metal servers, on virtual machines, in containers, or even in the public cloud, and a variety of different public clouds as well. Now, when I talk about a bare metal server, it's any commodity x86 server running Linux. The load balancer basically takes over that server, almost functions in a very familiar notion to most of you, which is that it can essentially be an appliance at that standpoint. And what it does is it provides load balancing services to back-end applications. And in addition to that, every one of these load balancers also sends telemetry back to the controller about the application's real-time performance. So in addition to providing the SSL termination, the application acceleration, and the application security, the load balancers act as beacons that send real-time information about the application to the controller. Now, the controller acts as a central brain in the system and allows the big data engine sitting in it to compute real-time analytics about the application, things like round-trip times and so on, which we'll get into shortly. And then it basically is able to give that view to the administrators. Now, one of the other components that I want to talk about in this picture is this notion of automation that is built into the platform. Because the controller is integrated with a variety of management and orchestration frameworks, it is able to control the back-end applications as well, which we'll see shortly. But the controller is automatically integrated with VMware's vCenter, OpenStack, Cisco, or VMware NSX, and so on. It allows it to use REST APIs to control the infrastructure components for these load balancers. So without much ado, I want to jump into the considerations involved in what you have to think about before you refresh your load balancers. The consideration number one is automation and self-service. We had Andrew Lerner of Gartner have a recent blog post in which he talked about how organizations need to invest in automation and agility in their business in order to meet the needs of modern digital business models. Now, if you look at it, the challenges that most enterprises have is that they have a slow time to market, and because of the frustration of application teams with provisioning VIPs and provisioning their applications, you have the problem of shadow IT with app developers saying that it's much faster to go to the cloud than wait for the IT team. This is one of the key reasons that you want to be able to invest in automation and self-service in your infrastructure. Think about how much time it takes for you to provision a new virtual service, or if you can enable your developers and testers to automatically self-service themselves when it comes to provisioning and maintaining their own load balancers and VIPs. Can you potentially consider a per-app load balancing model where you may separate the load balancers for the dev and test context from the production load balancers and automatically allow your developers to get a view of the VIPs that they have configured and bring them up and down at will without affecting the production instances, for example. So those are important considerations for automation and self-service. So let's take a look at the next one. Elasticity is a key need, obviously, for enterprises. When I talk about elasticity, it's a very common thing that you hear from load balancing vendors where they'll tell you that, yes, you can easily add capacity to your existing load balancer. All you need to do is just add another appliance. The challenge with elasticity that most organizations need to address is not just elasticity to scale up your load balancer in terms of making the pipe fatter, if you may, but you also need elasticity to handle a large volume of transactions across several applications, and that horizontal elasticity becomes important as well. And in addition to that, you don't want a reactive approach to elasticity. You want a much more automated approach, back to consideration number one. So if you take a look at this graph here, you want a elasticity model where your load balancers are automatically scaling in response to your traffic. This is what we call predictive or zero-touch scaling of the load balancing tier. So as you can see here, the load balancers basically follow the traffic model and go from 1 to 2 to 3 load balancers and then scale back down to 2 when traffic recedes. Now, the reason that this is possible is that the controller automatically gets real-time telemetry about the application from the load balancers, and it's able to auto-scale the load balancers in response to real-time traffic events. Now, more importantly, though, the controller can automatically also spin or notify the back-end infrastructure orchestration platform, whether it's vCenter or Amazon's AWS or Red Hat or OpenStack, or even with a scripting tool like Ansible. You can automatically spin up back-end application servers because the load balancer is very aware of the application's performance, so you can automatically scale it. So key considerations are, can you also trigger the backend application servers automatically? So let's take a look at the next consideration involved, and this is about application visibility and analytics. One of the key insights that Avi's founders had about 4 years ago is that your load balancer actually occupies a very strategic and important position in your data center. It is actually sitting in the path of application traffic, and it is in a unique position to be able to make decisions based on the application's performance. But most of the hardware load balancing vendors are so focused on delivering packets from one end of the network to the other that they cannot spare CPU cycles for these types of analysis, in the appliance itself. So Avi's architecture uniquely allows us to be able to leverage the position of the load balancer. And here's how we do that. So the load balancer itself sends millions of bits of real-time telemetry information to the controller. And the controller basically analyzes that information, and we are able to provide a picture that you would have never seen coming from your load balancer. The first thing that I want to draw your attention to is this round-trip time graphic that I have at the top. You can actually tell the precise amount of time that it took an end user to reach the edge of your network, and then from the load balancer to the backend server, and then from the server to the backend application, and so on. So this level of granularity in terms of a transaction's performance is something that is very useful for administrators to debug application issues, troubleshoot challenges of connectivity, and things like that. So key questions that you need to ask here of yourself is, what will real-time analytics about your application in the network context give you by way of power to solve problems in your environment? Will it simplify your job if you had clear end-user information and security insights? Can you actually rewind and go back in the last 15 minutes, last 6 hours, day, week, or so, essentially use your load balancer like a network DVR and look at every single transaction that happened and what exactly went wrong at a particular instance in time? So those are key questions to ask yourself. So let's take a look at the next one, which is around the whole notion of price performance. So a lot of times you hear that the reason that you need a custom hardware-based appliance is for the reason that you cannot compromise the performance of your load balancer. There was a time when this was true, way back about 10 or 15 years ago, but right now, if you look at the performance improvements in the x86 world, in the Intel architecture servers, over time, the price-to-performance ratio of these processors and Intel servers has improved so dramatically, not just because of better processors and better memory handling, but also because of toolkits like Intel's DPDK, the performance improvements in the network cards, and so on. All of these have contributed to a significantly better performance that the web-scale companies are able to take advantage of. So how does that translate into the load balancing world? The picture that you see here shows you the bare minimum load balancer that you can deploy, say, with Avi on, say, a bare metal or a virtual machine is a single SE on a one-core server can give you 5 gigabytes of SSL throughput, about 2,500 SSL transactions per second. Now, the flexibility with a platform like Avi is that you can go up and scale that appliance up by adding and making it more beefier. Now, you can also scale it out on the horizontal axis by adding more service engines that can essentially serve to provide additional processing power for you for your VIPs. So in this case, scaling up, you could go all the way to a single SE on a 36-core, 2-socket Intel server that essentially has 40 gigabytes of throughput using 4 10-gig NICs with essentially a 74,000 SSL transactions per second that you can achieve with a single server in that context. Or you can scale out the platform horizontally by adding more SEs that or service engines that basically give you that extra processing power essentially to scale to a very large footprint of service engines that you may want to use for all your applications or a single application as the case might be. But the notion that I wanted to communicate here to you is that the overall fabric's performance can be as high as 4 terabits per second, and millions of SSL transactions per second. So the scalability of the platform is infinite in that sense. So the next consideration is around whether you can handle the hybrid cloud scenario. How do you provide load balancing services today if you have to move to the cloud? You'd have to think in terms of providing a virtual edition of your hardware load balancer at a high cost and host it in Amazon or in Google Cloud, etc. Or you can choose a completely different load balancer from the cloud provider itself, at which point you're looking at a fundamentally different architecture for your application in one context versus the other. Would it be great to be able to have a scenario where you're hosting your application in your data center, and as capacity needs grow, you spill over that extra capacity into the cloud, maybe during Black Friday or Cyber Monday as an example, and then you're able to bring that traffic back into your data center when traffic recedes. So that's a scenario where you can still maintain that central control here. The controller has that visibility to both your cloud instances as well as to your on-prem instances, and you effectively are treating the application as treating the cloud as an extension in terms of where the application is hosted, and effectively burst to the cloud with intelligent traffic management that handles traffic across the board. The next consideration that I wanted to talk to you about is ecosystem integrations with the platform. Clearly, one of the major things that you want to be thinking about is where are you going to deploy your load balancers. It's no longer possible just to say that I'm going to put the load balancer in a rack and it's going to effectively provide application delivery services for all my back-end N-tier applications. What's going to happen if you are going to develop microservices applications with containers and maybe choose a platform as a service model? How do you integrate with back-end, private cloud frameworks like OpenStack or PaaS platforms like OpenShift? How can you? I alluded to this notion of automatically scaling up your back-end application servers. How do you trigger that? Where if you tell vCenter to spin up more workloads of a particular application because the application is getting hammered, you need to be able to automate that process. So your load balancer can be the trigger for that. So Avi has direct integrations through its REST APIs with a variety of these platforms, and it minimizes the administrator's headaches in terms of having to manage the automation of application components. So consideration number 7 is the total cost of ownership for your load balancing infrastructure. Typically, if you want if you look at this picture here, if you want a decent high-performing load balancer, you're looking at paying a fairly significant amount of money. The load balancer here, the traditional load balancer here, cost this particular customer upwards of $4 million when you actually look at the product and support, the cost of Intel servers, the separate cost of application performance and network performance management tools that they had to invest in, and then the disparate management of these appliances that they had to deal with. Now compare that with Avi. It was a saving somewhere in the ballpark of between 65 to 75%, simply because there is no proprietary hardware involved. You will see shortly when Ashish demos the product to you about the power that you get from the analytics in the platform and what that saves you by way of headaches when it comes to troubleshooting, when it comes to understanding the application and being prepared for unexpected traffic events and so on. So without much ado, what I want to do is pass the control to Ashish to share a demo with you. But as you think about your refresh cycles, keep in mind some of these considerations, and we'll revisit them here shortly after the demo. Ashish, I'll let you take the demo, and then we'll loop back to finish up.
Thanks, Chandra. So what I'm going to do now is actually show you some of the capabilities that Chandra talked about with Avi Vantage platform here on a demo, on a live demo. What you see here on my screen is Avi's web console or the web UI, which is using REST APIs to talk to the Avi controller. What you've got here is a centralized Avi dashboard across your entire infrastructure, giving you an application-centric view into the load balancing environment. So unlike traditional load balancers, which will show you the load balancers, which are up or down, etc., we show you how your applications are doing. And the applications are color-coded by the health score. So every application has a comprehensive health score, which consists of the performance of the application, but also resource utilization, any anomalous behavior, as well as security considerations and DDoS attack, etc. There is another view that I want to show you, which is a tree view, which shows you the entire infrastructure of your applications that it's deployed on. So for example, in this case, this demo of the applications is running on this particular service engine, this particular load balancer. It has a pool of three pools of servers doing content switchings across, and the list of servers that the actual application is running on. It also shows you the health of the individual application VMs. In this case, one of the VMs is down because the health monitor is not able to resolve ARP. Very central, easy to understand view on your application's health and performance. Now let's go to the second step of the demo, in which I'm going to show you how easy it is to add a new application instance, new virtual service or VIP on Avi Vantage platform. Compare this experience to what you do with your traditional F5s and NetScalers, where it might take days or many times weeks to spin up a new application instance, new VIP. Right, because you need to worry about peak capacity planning, maybe procure new devices, do network plumbing, do tenancy and security assessment, wait for the maintenance window, etc. All of that goes away with the self-service. So I, as an app user, an app admin, can log into this web console, to the Avi UI, and in my own tenant, spin up my own application. So we'll start with the basic setup. That's because I've already templatized most of my parameters in terms of what application, HTTP and other application template information I want to use. So let's start with the basic setup. The first question that I get asked by the Avi UI is, which environment do we want to spin up these virtual service? That's because the same Avi controller is managing multiple different clouds, on-prem vCenter, OpenStack, a container cloud, and a bare metal environment, as well as a public cloud such as AWS. For now, let's start with the vCenter environment. So we select that, and now we are ready to configure our virtual service. So for now, let's just call it webinar app. We'll make it HTTPS so that we can have secure communication. Select an SSL certificate. Also, let's configure an IP address, or with the DNS integration that we have, you can just type in a name, and it'll select an IP address automatically. That's it. My front-end configuration is done. Let's do now the actual pool member addition. Again, you don't have to remember the IP addresses. In the fully automated and intelligent environment with Avi, the Avi controller actually talks to vCenter, gets a list of all the networks or the port groups that are available in this vCenter. In this case, I know as an app admin, my application is running in VLAN 100. I select that. I see a list of all the VMs running in that VLAN. Okay. I know I'm trying to load balance a web tier, so I search for web. I see 3 VMs, which are in my web tier. I add those servers, and that's my pool. That's it. And then I say save. And now what I have is I've configured a virtual service that is running on this specific service engine. I did not select the load balancer or the service engine to place this VIP on. Avi controller was intelligent enough to first of all figure out, do I need to add additional capacity? Do I need to spin up another service engine? In this case, it didn't, because there was enough capacity available. So it reused one of the existing service engines. Then it ensured that the service engine VM had right network connectivity. If not, it added those VNICs into the right port groups so that it can communicate to the pool servers, but also it can communicate on the front end to the clients through the VIP. All of that was done automatically. Then the Avi controller downloaded the VIP configuration, the virtual service configuration down to the service engine, and it's ready to receive traffic. So it took us 30 seconds, not days or weeks. Let's actually run some traffic, right? So I'll go ahead on my browser, and I will run some traffic on this virtual service. So let's wait for this virtual service to come up. And once this comes up, what you will notice is that on this screen, and let's make it real time, you will be able to see the actual traffic. If I go back to my tab, yes, the actual the URL name, host name doesn't match the SSL certificate. That's why it's giving the error. We skip on that, and you'll see Avi's website running behind this virtual service. All right? Let's see this traffic on my browser, on my web UI. Right there, I have a spike in my traffic. It shows me end-to-end latency information. We'll talk about that in the next step of the demo. But let me go to the log screen here and show you that this traffic did come in. I'll open up one of them. So in this case, for example, this particular transaction shows that I'm running on my internal network on a Mac OS, running a Chrome browser on my computer with TLS 1.2 version of SSL TLS with perfect forward secrecy with ECDSA. So the complete information about the client that the user is coming on. This is the IP address port that I logged in from. It took 27 milliseconds for my browser to hit my lab, the load balancer that's running in the lab. From this load balancer, this is the backend IP address and port that is used with the source NAT. It took 1 millisecond to hit the backend server. It was server number 3 out of the 3 that we added that served this request. The request itself was a video asset on the website, and it took 98 milliseconds for the application to generate, the web server to generate the video result. And then it took 135 milliseconds for the data to go back on the wire to my browser. It was about a 3 megabytes file. As you can see here, every single detail of my transaction is captured here. Without any agents, without any monitoring fabrics, I have detailed visibility into my transactions. Now, you might ask that, well, this is good. This is a load balancer. What about the advanced features? I am used to my iRules on F5 or other advanced policies on my NetScalers. Do you even support those? Oh, absolutely. In fact, it's much easier to do those kind of advanced policy than your traditional load balancers. So I click on the Edit button, and here is where I can create all the advanced settings that I need to. In this case, I'm going to go ahead and add, I can add a network security policy or an HTTP security policy, a request or response rewrite, or a Lua-based scripting for advanced use cases. But about 90% of these iRules or equivalent policies are handled by Avi's native policy engine. You don't have to write complex rules. Let's actually see that in action. So let's go ahead and create a security policy. I'll add a rule. We're going to call that a block PHP rule. So it's a sample rule where I want to match, and I can match on any parameter in my header. So I want to match on the path parameter. And I can have any flexible matching criteria. I can do even a regex pattern. But I want to say that if it ends with, let's say, PHP, and I can add multiple matches, by the way, multiple rules. And I want to select an action. I can send a local response, redirect, rate limit, whitelist, or in this case, I want a blacklist. I want to close the connection. Okay, that's my rule. It took me 15, 20 seconds to set this up. And now let me go ahead on my the browser request URL, and let's just create a request that says demo.php. There you go. I got an empty response, which is expected. Let's actually see that in action. So I'll kill my query here, and I will right here I can see that a request came in with demo.php as the URI. The Avi service engine generated a local response. Basically, closed the connection, so the request never went to the backend server. And the reason it did was because it matched the security rule that we just created called block PHP. So what you see here is that not only it's easy to create such a rule, unlike your complex iRules, it's extremely easy to see it in action. That's very powerful. Now let's go back and go to a few other aspects. So we've covered so far how easy it is to spin up a new load balancer and create new rules on that. Let's move to some of the analytics piece of the demo. So I'm going to move to a different virtual service, different application that I'm running in my lab. It's called demoavi.com. What you see here is that the first thing as I click on this demoavi.com virtual service is the end-to-end timing dashboard. And what this is telling me is that over the last 6 hours, and I can change that to real time, day, week, month, year, whatever window I want, what is the latency experience as my users are seeing it. So in this case, on an average, this is the average value, and you can change that to peak or current, etc. The average latency from my clients to the load balancer, which is coming over the WAN, it's about 94 milliseconds. The average latency from the load balancer to the server, so this is your local network latency, round trip, it's about 1.5 milliseconds. So these are two network latencies, WAN and local network. The third component is the application latency. So this is how long the application is taking to generate the response once it receives the HTTP request. So we're able to identify the application latency without any agents, without any monitoring fabric or span ports, right? Just seamless as a load balancing solution. About 39 milliseconds. And finally, the time it takes for the whole response to traverse over the wire, so it's a measure of the bandwidth, it's about 4.2 milliseconds. So on an average, my users are experiencing about 139 milliseconds of round-trip latency. Now that's average. You can actually go back in time and say, okay, what happened at 8 o'clock this morning? Why is there a spike, and why is there a anomaly button here? Well, you notice is that the latency spiked up from 139 milliseconds to close to 167 milliseconds. And in this case, we also tell you that based on the color code, you can visually see, you can also see in the number, is the application latency that more than doubled. So it used to be around 30-odd milliseconds, went up to 68, 69 milliseconds. So in this case, yes, there was a latency spike, but it was not the network issue, it was the application issue. Maybe there was a log rotation that was going on between 8 and 9 a.m. this morning. Compare and contrast this to how you do troubleshooting today. Today, if there's a performance issue, usually, the network team gets blamed. It's always the network, right? Well, no. Such a tool tells you where the problem might be, WAN, local network, application, or bandwidth. Instead of doing like getting in a war room and doing finger pointing between the network and the app and the server and the WAN team, you can actually, any of them, the network admin or the app admin can do self-troubleshooting without opening up tickets, without doing TCP dumps and waiting for the problem to be replaced. This is an extremely powerful troubleshooting tool. As some of our customers call it, mean time to innocence tool. All right, so by the way, we also have other screens, just throughputs and connections and requests and so on. Right? But the other thing I want to show you now is, this is a 40,000 view. On an average, what's happening to my application? What if I want to see individual logs? We saw this earlier on the new virtual service we created, but let's look at this one, which has a little bit more data. So in this case, the same application, same demoavi.com, I've clicked on logs screen. And what you see here is that we have 30,000 logs that we have collected. Individual logs, let's see what it looks like. So let's open one of them up. Again, same video URL. In this case, this request came from Nigeria with somebody running on a Windows 7 machine. Some other information here was the transaction latency at every stage of the network, which backend server responded to that, etc. Again, geographic information of your clients. With a Google-like search bar, you can do contextual search as well. You can say, show me only all the transactions coming from my phone. Well, these are all the transactions coming from my phone. This one's coming from Saudi. If you're a network admin, if you're interested in finding out what is the end-to-end latency breakdown of my application, well, you click on the end-to-end, and you will see a nice bar chart of different latency intervals. As you expect, most of the transactions are sub 100 and sub 200 milliseconds, a few sub 400. This is all good. The chart is going down, except there's a big spike at the 800 plus milliseconds. That's never an okay situation, so let's troubleshoot. Let's debug what's going on. Compare yourself again to coming in the office in the morning and seeing these tickets saying performance is an issue, something is slow. How do you handle today with your traditional tools? It's a very painful, very complex situation. And compare that to what I'm doing here, which is I just clicked on the high latency filter. So I have about 1,800 logs with high latency. Then I can do second-order analytics. Is this high latency coming from a specific browser? It doesn't seem so. Is it a device compatibility issue? It doesn't look like. Maybe it's a specific location that's affected. Yep, except for one transient request, almost all of the requests are coming from India. All right, that's something important. That's good to know. Now, the final piece of the puzzle that's remaining is which component of the latency is high. So in this case, you can actually visually see from here that's a yellow bar color in this latency bar, which is slow, and the yellow is the WAN latency. So within a few seconds, what I've actually showed you is that I can figure out where the high latency transactions are coming from, what the root cause is. In this case, it's maybe an upstream router or on your Indian data center, or maybe the WAN link itself is busted. Extremely powerful troubleshooting capability. Let me move to some of the security analytics as well. So if I kill this filter here, and if I look at the SSL information right here, it shows you what are the different profiles, security profiles of the requests coming in. In this case, most of them are TLS 1.2 and so on. Right? Again, very important to find out how your traffic is doing. On the security front, actually, I'm going to move to a different application now and show you a couple of more things. So in this case, I'm going to show you some more security insights. So we have a security insight screen. It tells you what are the different certificate types that your clients are coming on, what are the different TLS versions, what is the SSL score of my application. So we measure whether the PFS is enabled or not, whether you have a weak cipher or a strong cipher, is your SSL certificate about to expire. If so, we can automatically renew the certificate by integration with the PKI server. And the final screen on the security side is the DDoS attack. So I click on that. It shows you what type of DDoS attack, if anything, that's going on. We can detect a few dozen types of different DDoS attacks. In this case, is a layer 4 SYN flood attack, which IP addresses it's coming from. I can block this with a click. And by the way, this UI is using REST APIs underneath, so you can completely automate that. We can detect DDoS attacks. You can trigger events based on certain thresholds. You can not only block traffic at the load balancer layer, but you can generate triggers to your external routers and start cleaning and blocking the traffic right at the edge of the network. Extremely powerful. The final piece of the demo on this particular application I want to show you is the scale out. So let me go to the analytics screen. Let me look at the throughput, and I'm going to look at the real-time information on the screen. So what you notice here is that I have this virtual service, it's called Scale Out Virtual Service, appropriately named, is running on one service engine. And these are the various ports it's running on, what are the SSL certificates, etc. Now, imagine that you have a Black Friday or a Cyber Monday kind of an event, and where you need to add additional capacity. Instead of adding additional hardware or software appliance pairs, waiting for days or weeks, what you can do with Avi is automatic scale out. Right, as the traffic grows, you can automatically add more load balancing capacity, and as the traffic shrinks, you can scale it back. For the purpose of the demo, I'm going to do an API-based, or in this case, a UI-based scale-out, but the same thing can be done based on automatic traffic-based triggers. So what you notice here is that you have about 400 Mbps or so traffic running, and if I click on the button that says scale-out, what's going to happen in the background is the Avi controller is communicating with the service, with the vCenter. It's creating a new service engine. It's adding new VNICs to that VM. Again, communicating to the vCenter, adding the right VLANs and the IP addresses, both for the front end and back end. Download the virtual service configuration. It happened in front of your eyes in a matter of seconds. And now we have gone from this virtual service running on one service engine to 2 service engines, and your performance has almost doubled. This is the power of software-defined elastic load balancing solution. Within seconds, I can add additional capacity in form of additional VMs, additional bare metal servers, additional containers. I can add additional capacity on-prem. I can add additional capacity in public cloud, so that I can do cloud bursting if I needed to do so. This is impossible to do with your hardware load balancers. Why? Because you have to procure them, manually connect them, and there is no centralized controller. There is no distributed data plane fabric the way Avi has. On the final note on my demo, I want to show you one last thing, which is Avi's applicability in the next generation container-based fabric. So I have another demo system here where I moved to a different tenant where I'm running my Mesos Marathon cluster. And what you see here is that in a container-based, microservices-based environment, I have about a dozen or so different microservices running that consists of, that builds the e-commerce app, which is photo.com, which is right here. The external users come in to photo.com, think of this as a Flickr or a Google Photo-like website, and then they can purchase their photos or accessories. So the actual application, unlike a monolithic app, consists of microservices so that each microservice communicates with each other, and they have different number of containers behind it. In this case, the bubble size represents how many containers they have. The larger the bubble, the more containers they have. And the color and the health score represents the application health score, very similar to what we saw earlier. The difference here is that we not only provide all the load balancing and analytics as SSL services, we automatically build this application map. It tells you how each microservice is communicating with the other and builds this dependency map, right? So you have understanding of how they're talking to each other. For example, if I click on one of them, again, you see the same screens, analytics, the logs, all of them available here, but what's different here is the application map. So in this case, the catalog microservice is talking to sales microservice. The latency is 108 milliseconds on an average, and the two other microservices, marketing and inventory, are talking to catalog service. Right? I can change these parameters and look at throughput. I can look at errors. I can look at multiple different parameters. But not only that, I can actually do on-demand whitelisting and blacklisting and microsegmentation. So for example, let's say I do not want marketing to talk to catalog at all, right? So I go and say secure the VS, and you see we have automatically built the whitelist, blacklist based on existing traffic. But I say I do not want marketing to communicate anymore to the catalog service, and I save. And now what you'll see here is that the same catalog microservice has a blue circle behind around it, which means it's been secure. And now if the marketing service tries to communicate with catalog, it's being actively blocked. And that's what the red arrow indicates. And if I go back to my dashboard, you will set that in the large screen as well, where marketing can no longer communicate with catalog service. So as you move your workloads from your traditional on-prem or even virtualized environment to public cloud and container environment, think about the power of Avi's platform, Avi Vantage platform, where it gives you the full layer 4 to layer 7 services on bare metal, virtualized, public cloud, and container-based environment without having to learn different operational experience, without compromising on different operational model, different feature sets, etc. With that, we'll pass the ball back to Chandra to wrap up our webinar and discuss a few takeaways. Chandra, back to you.
Thank you, Ashish. Folks, hopefully that gave you an idea of how these considerations that I talked about earlier in the demo should influence your purchase decision for load balancers. I want to quickly recap with a few key takeaways, what I call the 7 habits of highly effective load balancers. So let's take a look at those and see what we should be thinking about. The first, of course, that I talked about is automation and self-service. This is super important, folks, as you develop newer application models, as you create a much more agile delivery model in your enterprise, definitely think about how you're going to automate your infrastructure and provide self-service to internal customers. The other part is on-demand elasticity. The days of over-provisioning and overpaying for our load balancers should be in our rearview mirror. We should be looking at solutions that allow us to grow and shrink elastically, and as Ashish shared in the demo, in response to real-time traffic parameters, and offer you that API-based way of being able to do that. The other thing is application visibility and analytics. Why invest in having to do TCP dumps and export logs and so on when you can have your load balancer be the source of that information? So the other part, of course, is choose a load balancing solution that delivers the best price performance for your money. Most importantly, load balancing is dramatically changing as you have a lot of these Mode 2 and microservices-based applications. Can you imagine putting a hardware load balancer in front of every single container-based application? That would be not only cost prohibitive, but frankly, quite impractical. So let's also take a look at the next consideration around hybrid and multi-cloud environments. Every enterprise, even if you're not fully moving to the cloud, you have some footprint in your data center, and perhaps you want to run your dev and test workloads in the cloud. How do you make sure that you don't have to retrain your administrators and effectively use a consistent architecture both in your data center as well as in the cloud? And in a situation where you need to do this, where automatically you can burst to the cloud in response to a Black Friday or a Cyber Monday type event. How the highly effective load balancers also are software defined, and they are infrastructure agnostic. You don't want software defined hardware. You don't want something that is like software. You want a truly software defined architecture that allows you to play in any environment, whether it's VMware, Mesos, or Kubernetes, or Red Hat, as the case might be. The other and the most important thing is load balancing services should allow you modern load balancing services and application delivery models, like we just demonstrated to you, should allow you to lower your TCO for application services. Now, lowering the TCO, as I showed, comes in the form of reducing your total product and support costs, but also improving your operational efficiency through that central management, through that ability to provide visibility and analytics, and the ability to have a much more self-service and automation-driven model. With that, I wanted to share with you a place where you can go to contact us to get a custom demo. We'll take a couple of questions before we leave. Ashish, one of the questions that came up as you were doing the demo was, how do you handle complex service additions such as content switching? Do you want to take that?
Sure. We showed part of the demo where we were able to add a new security policy, an iRule equivalent, in a matter of seconds. Again, the same operational model, you can easily add a content switching, request-based, URL-based content switching in extremely easy fashion. And the other piece of it is you can actually see that happening in action with a log screen. You can create a content switching policy, and then you can see that in action as soon as you've created that.
Great. One other question that I'll take a quick stab at here is how do you license the product? And what I wanted to talk about here is one of the great things about a software-defined solution like Avi is that it allows you to consume your licenses in a very flexible way. So let me explain. So Avi is licensed based on a per vCPU basis, so you can install a single Avi service engine across 36 vCPUs on a single box if you wanted to, or you can spread it on 36 individual servers, each running a single service engine or load balancer. This is what allows you to provide true multi-tenancy if you wanted to provide dedicated load balancers to separate business units, so there is no noisy neighbor issues. You can also make a single load balancer higher capacity if you so choose to do that. So from a licensing standpoint, it's a very flexible approach to deploying your load balancers. We have a lot more that we can share for you guys. I know we are almost out of time here. We'd love to be able to respond to some of the other questions that have come up here directly. We also encourage you guys to get in touch with us before you get ready to make your next load balancer purchasing decision. We'd love to be able to share a custom demo and share with you how we're able to solve very similar problems for the largest of enterprises and the most demanding application delivery use cases that are out there. So with that, thank you very much for joining our webinar today, and look forward to talking to you in person. Thank you very much.